Hello, and welcome to Game Revolutions, the series where I take a video game that I started writing in high school and blah 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 blah. If you've been watching the previous episodes, you know that I've been on a bit of a speed kick.
I feel the need
to optimize the performance of my Coco games. Ow! And if you watched the most recent video that I released, you know that I've been exploring these bad guys. So that gives you a bit of a hint as to what's coming up in this episode. David Ladd wonders if by using the basic joystick routine from the ROM, I'm wasting cycles. Is it doing too much? Curtis Boyle thinks so. He says that since you aren't using analog-style controls, you can write your own routine, rather than using the basic ROM call to speed it up in a few ways. Only check the joystick and axis you actually need, and don't bother sampling all 6 bits for an analog result. I only care about extremes. Am I very close to the left or very close to the right? Eventually I will care about up. I won't even care about down, but it's still the same axis. But still, I could speed that routine up by customizing my own routine to do the things that I want to do. If you haven't seen this previous video on mine that does a deep dive into the joystick, I highly recommend that you pause now and watch that. I will be building on all of the things that I have discovered in that video in this video. So please, take some time. I'll wait right here. Thanks for those comments on YouTube. They led to my whole investigation of the joystick in the first place. And they mentioned a couple areas I could improve upon, and my investigation confirmed that. So to summarize, there are actually 3 places I can look at in this original code. This is taken directly from Unraveled, but I have renamed some of the labels to make it a little more clear. Thing number 1 is this. I don't need all 4 axes. If I'm using only one joystick at a time, I only need 2 axes. Thing number 2, retrying 10 times to get the same value you got the last time this was called. I don't want to do that. I don't need to do that. And thing number 3, this whole loop that gets a full 6 bits of attempted precision of the joystick. I don't need that. I just need to know if it's on the left or the right, or up. Thanks to Simon Jonason, who posted his version of the joystick routine that he used in one of his games onto the Coco Discord. So I looked at that, I looked at the original code, and based on what he wrote, I came up with something very similar. We'll come back to this stuff at the top a little bit later, but let's look at the meat. So first I'm going to measure the x-axis of the right joystick. And I no longer have a loop where I keep measuring and measuring and measuring and coming up with guesses that get narrower and narrower and narrower. I just have a couple of thresholds. So my left side threshold is 16. That's about a quarter of the travel space from left to right. Similarly, my right side threshold is 48, which is also about a quarter. In order to make this a guess, I need to shift it to the left twice, because I'm sending it to the DAC, and the DAC only uses the upper 6 bits of the hardware register. And I'm going to OR in a 2. This ensures that the RS-232 bit is set to 1, which means the printer should not wake up and whatever we're doing here won't affect it. And that gives me that binary value. So I send that out to the DAC, which then goes to the comparator. I immediately retrieve the result, which will be in the high bit of that hardware register. So branch on plus would tell it to branch if the high bit is 0. A high bit of 0 means the comparator returns 0, which means the joystick is less. So if the joystick is less, I'm going to write a 1 to that memory location, and then I'm going to move on to doing the y-axis. Otherwise, I need to test the right threshold. So I fill A with the right threshold, send that to the DAC and out to the comparator, retrieve the result, and if the comparator returns a high, that means a 1 in the high bit, and that means that A will be negative. So on minus, I'll branch to here, and I will store a 2. So 1 means it's on the left, 2 means it's on the right. Otherwise, I fall through to here and clear it to 0, which means it's in the middle. And in either way, I'll fall through or branch to the y-axis. This is even shorter because the only possible values are up and not. So once again, my threshold will be about a quarter of the travel. And if the comparator returns low, meaning it's a positive number, there's a 0 in the high bit, we'll go to here. And we'll put a 1 in JOYRY. Otherwise, we put a 0 in JOYRY. And that is it. There is no loop. Now let's take a look at that code we skipped. We need to talk to the PIA to tell it which pin of which joystick we're sending to that comparator. We're going to be caring about the right joystick pin 1, which gives the x-axis, and the right joystick pin 2, which gives the y-axis. In both cases, that means CB2 needs to be 0, so I can just set that to be 0 once. And it's the CA2 that I need to change, so it'll be 0 for the x-axis and 1 for the y-axis. So at the top, when I measure the right joystick x-axis, I will set both CB2 and CA2 to 0. That means I need to add a 0 into that bit there. You can find a deeper explanation of controlling the selector switch in the assembly language sound series. And then when it's time to measure the y-axis, the only thing I need to change is CA2. I change that to 1 by ORing a 1 into that bit. And that only leaves a few lines at the top to discuss. This ensures that whatever I'm sending out to the DAC doesn't go out to the TV speaker. So I take the master select switch and I turn it off. Let's do a comparison of cycle counts between the original JOYIN and my code. Yes, folks, that means it's time to do arithmetic. Yay! So this is my copy of the original JOYIN code. I'm going to be chunking it up into pieces because there are loops nested in loops nested in loops. So every time you see a pragma CC, that means I'm resetting the cycle count total so that I can separate things out into chunks. So I start counting after this. I'm not going to be counting all this stuff where we're talking to the multiplexer and talking to the PIA, just to be nice, and it's a little easier to avoid it. So I'm not even going to count this, and I'm not going to count this when we change which joystick pin we're looking at, which happens 4 times. I'm just not even going to count them. So the total amount for JOYIN will consist of these instructions plus whatever it takes to read one axis and that whole loop. So the full number of cycles it takes to do JOYIN will be 5, this part at the beginning, plus this whole read one axis loop. I'm going to leave that as a chunk and I'm going to drill down into that next. The read one axis loop consists of these 10 cycles at the beginning, and this tri-axis 1 loop, however long that takes, that brings us down to here, plus another 19 cycles. I'll just ignore the RTS. But this whole thing happens 4 times. This loop is governed by B, which starts at 3 and goes down through 0. So now we need to drill down into tri-axis once, that entire loop. So tri-axis once has these 3 cycles here. It has this test bit loop, however long that is. And then it has another 21 cycles here. And that full quantity is multiplied by 10 because this loop is governed by those 10 tries. And so that leaves test bit. How long is test bit? That loop is 44 cycles times the number of times we iterate, and that is 6 times. And that's because the A register starts at hex 40, and it goes down until it hits 1. But to be more precise, at the end of the loop, the very first value it will have will be half of 40, which is 20. And that's because at the bottom of the loop is when we will divide by 2 and compare. So the first iteration has it going down to 20, and then the final iteration has it going down to 1. And from hex 20 down to hex 1, that's 6 times. So now we can fill in the values. Test bit 44 times 6 is 264. We plug that into tri-axis once. That brings us up to 2880. We plug that into read one axis. That brings us to 11,636. And then we add those 5 extra cycles for a grand total of 11,641. This is almost an entire field doing nothing but reading the joysticks. But This kind of rarely happens. It is rarely the case that JOYIN is called and the value has changed. So in the best case, in fact, in the typical case, try-axis once isn't multiplying by 10, it's multiplying by 1. That will give it a total of 288. Plug that into read one axis, and that will give it a total of 1268. And then add the extra 5, that gives us 1273. Now we're down to about 22 scan lines. Still slow though. How about our new routine? The cool thing about the new routine is there are no loops, so there's no complicated counting. There are some conditional branches, but I'm going to be super lazy and I'm going to double count. I'm going to count the then and the else clauses. I'm also going to count messing with the P, which I didn't count in JOYIN. So I'm being very unforgiving with my code, whereas I was very forgiving with JOYIN. And I'm just going to lazily add everything up and see what we get at the end. 144. 144, that's about 2.5 scan lines as compared to 22 scan lines in the best case of JOYIN, or a full field when JOYIN detects that the joystick has moved. And recall, my routine doesn't care if the joystick has moved or not. It's always going to be really under 144. But the question now is, does it work? Now I call getJoystick toward the top of the main loop, and it's responsible for filling in these 2 bytes. And for now, the only time that I'm actually using those values is in copy car. I first check to see if we're jumping, and if that's 0, then that means we're not jumping, so I go here to say that we're not up. Otherwise, I haven't added the jumping code back in yet, so I just put a little stick of red up in the yellow region at the top of the screen, just to indicate that I know that you're trying to jump. And here you can see the Unraveled series and the Color Basic ROMs are starting to rub off on me, and I'll just skip over this line that would, instead of using red, would use yellow. And in both cases, that red or yellow stick will go at an offset of 33 from where the off-screen graphics buffer lives. And then it's time to do the sliding. So I now check the JOYRX. If it's 1, then we adjust the car to move to the left. If it's 2, we adjust the car to move to the right. And there isn't any change to this code from before. And we'll try going to the right. Very nice. To the left. Very nice. And if you keep your eye up here, you'll see what happens when I try to jump. Go up, 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 up. Okay, good. Now, one thing I'll mention is that I'm using the keyboard as my right joystick. And at some point, I'll be using my Xbox controller as my joystick. But I really do need to test with the actual analog joysticks on my real Coco. What you're seeing right now is XRoar. And I'm going to be doing that after I've added some more game elements and I can actually play around with that in context with actually trying to overcome obstacles and stuff. Now, do we get any gain with the scanline situation? If I use MAME, what will MAME tell me? Once again, I'm going to set a breakpoint just before the sync at the bottom of the loop, and that is at 3E80. Skip over the first few times it hits that. Okay, so before we were getting about 136, 137. I'm now seeing 109, 110. Jeez. That's pretty amazing. And I should mention that when I was getting 136, 137, I wasn't actually changing the joystick. It would be probably much slower if I were. And here I'm not changing the joystick either, but even if I were, that doesn't affect the performance. So this is pretty great. Again, I don't know for sure how well this is going to work until I play test it with the real joystick and like the rest of the game added. But I'm liking these numbers. So until next time, thank you for watching. The series where I take a video game that I started in high school and I blah, 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 blah. If you've been... Hello, and welcome to Game Revolutions. Hello, and welcome to Game Revolutions.